You know that most metals are found in nature in a combined state, owing to their high reactivity. Metals found in a combined state in the Earth's crust are known as minerals. Only those minerals that have a relatively high concentration of metal and can be extracted in an easy and cost-effective process are called ores. The only metals found in free or native state are gold and platinum. They are usually found along with earthly or rocky impurities such as sand and clay in the Earth's crust. The relative abundance of metals varies in the Earth's crust. The table here lists the relative abundance of some of the metals in the Earth's crust by weight. Of these, aluminium and iron are relatively more abundant than others. Aluminium constitutes about 8%, while iron constitutes 5.8% by weight of the Earth's crust. Thus, aluminium is the most abundant metal and iron the second most abundant metal by weight in the Earth's crust. Also, aluminium is the third most abundant element and iron the fourth most abundant element by weight of the Earth's crust. The table here lists the principal ores of some important metals and their composition. Both aluminium and iron are used widely in industrialized nations. Naturally occurring aluminium is a major component of silicates such as mica and clay. Aluminium is extracted mainly from its principal ore bauxite, since it is an economically viable source. Valuable gemstones, such as rubies and sapphires, contain aluminium oxides along with traces of transition metals as impurities. Rubies are crystalline forms of aluminium oxide, which are red in color due to the presence of chromium as an impurity. On the other hand, sapphires are available in various shades owing to the presence of impurities such as nickel, cobalt, and titanium. Iron is mainly extracted from its oxide ores, such as hematite and magnetite. The iron extracted from these ores is mostly used in the manufacture of steel, an alloy of iron. Iron is also an essential element found in biological systems. Other metals that are extensively used are copper and zinc. You can see from the table that copper and zinc are extracted from their oxide. Sulfide or carbonate ores. You already know that most metals are found in nature in a combined state. Metals that are found in a combined state in the Earth's crust are known as minerals. Not all minerals can be used to extract metals. Only the minerals that have a relatively high concentration of metal and can be extracted in an easy and cost-effective manner are used for extraction. Such minerals are known as ores. For example, bauxite is the principal ore of aluminium. The metal is extracted from the ore after a series of procedures and techniques known as extraction and isolation procedures. The main steps involved in the extraction and isolation of metals from ores are given here. Concentration of the ore, isolation of the metal from its concentrated ore, refining of the metal. The branch of science and technology that deals with the isolation of metals from their ores is known as metallurgy. An ore contains a metal associated with other undesired substances like sand, clay, etc. These undesired substances are collectively known as gangue or matrix. The process of separating gangue from an ore is known as concentration of the ore. It is also called dressing or benefaction. Metals can be concentrated from their ores using any of these methods: hydraulic washing, magnetic separation, froth flotation, or leaching. The choice of the technique used for extraction depends upon the differences in the physical properties of the compound, of the metal present, and that of the gangue, the type of metal, the facilities available, and environmental factors are also taken into consideration. Let's now look at each method in detail. The name hydraulic means operated by the pressure created by forcing water or another liquid. Washing ore with water is known as hydraulic washing. Gold mines make use of the hydraulic washing technique. An upward stream of running water is used to wash powdered ore. The lighter particles of the gangue are washed away and the heavier ore is left behind. This technique separates the gangue from the ore using the difference in their specific gravities. It is, therefore, also known as gravity separation. Magnetic separation is used when either the ore or the impurities in it are magnetic in nature. For example, separating iron from its ore, hematite. In this method, powdered ore is placed on a conveyor belt that moves over magnetic rollers. As the ore passes over the conveyor belt, the magnetic particles are attracted by the magnetic roller. The magnetic particles fall in a container below the roller, while the non-magnetic particles fall in another container that is away from the roller. Froth flotation separates the gangue particles from the ore based on the fact that gangue is wetted by water, while mineral is wetted by oil. The ore is crushed into fine powder and mixed in water. Then, collectors and stabilizers are added to the water. A collector is a substance such as pine oil or a fatty acid which enhances the non-wettability of the ore particles. A stabilizer is a substance like cresol which increases the stability of the froth. The mixture is agitated with the help of a rotating paddle. This draws air into the mixture and froth is generated. The froth is then skimmed off and is dried to recover particles of the ore. This is similar to the technique that separates butter from buttermilk. The froth flotation technique is mostly used for sulfide ores, as they are easily wetted by oil. It is also possible to separate two sulfide ores by simply adjusting the proportion of oil to water. At times, a depressant is used to separate two sulfide ores. A depressant is a substance that selectively prevents one of the ores from entering the froth. For example, if an ore has both zinc sulfide and lead sulfide, sodium cyanide is added as a depressant. It selectively allows only lead sulfide to enter the froth, but not zinc sulfide. Leaching is used when an ore is soluble in a certain suitable solvent. Let us consider the leaching of alumina from the principal ore, bauxite. The impurities associated with bauxite are silica and titanium dioxide. The leaching of alumina involves dissolution of the ore in concentrated sodium hydroxide at 473 to 523 Kelvin and 35 to 36 bar pressure. When the ore is dissolved in concentrated sodium hydroxide, the aluminium oxide reacts with sodium hydroxide and forms soluble sodium aluminate. The aluminate solution is neutralized by passing carbon dioxide gas. This precipitates hydrated aluminium oxide. The hydrated alumina is filtered, dried and heated to 1470 Kelvin to give pure alumina, that is, aluminium oxide. Another example is the leaching of silver or gold with a dilute sodium or potassium cyanide solution in the presence of air. Silver, when treated with dilute sodium cyanide solution in the presence of air, results in the formation of a complex called sodium argentocyanide. This, when treated with zinc, displaces silver from sodium argentocyanide and results in the formation of pure silver.